The next speaker is Maksim Zhukovskii from Moscow Institute of Physics and Technology, and he's going to speak about weak saturation and sparse random graphs.
Okay, thank you very much. Even on this slide, I already have one mistake because today is the 13th of April, not 13th of March. Yeah, let us believe that on the next slides I will have less number of mistakes. So yeah, my talk is about the weak saturation in GIF and P model when P is small. Let me start from several definitions. Recall the definition of weak saturation. So what do we have? We have a graph G, and its spanning subgraph H. And consider the following graph process. We consider sequence of spanning subgraphs of G such that every next graph contains the previous one. Here I denote them by H0, H1, H2, and so on. The first one is H, and the last one is G. So we start from given spanning subgraph, and we finish on G. And this sequence has the following properties that for every moment, the next subgraph minus the previous one contains only one edge. So it means that at every moment you add one edge. And this edge should create at least one new copy of F. So with appearing of a new edge, you get at least one new copy of F. And in this way, you get, starting from H, you get all the missing edges of G. If this process finishes on G, then we say that F percolates in G. And the minimum number of edges in such a spanning subgraph of G we call the weak saturation number. So we say that H is weakly F saturated in G if it contains if it doesn't have a copy of F and it F percolates in G, and if it contains the minimum possible number of edges, then we call the number of edges in this graph by weak saturation number and denoted by W sat of G and F. Okay, I believe that the definition is clear. Even I give here some picture where I try to show how red subgraph percolates in red and black subgraph. So we have our graph G, which contains all these red and black edges, and spanning subgraph H contains only red. It has 5 edges. It is a tree, and our graph F is a triangle. So at every moment we find a triangle like this that contains 2 edges of the current graph, and add one new edge. So we add this red edge. At the next moment we find another triangle that contains 2 existing edges and add one more, and so on. And it's easy to see that completing in this way we get all the edges of the graph G. And so the weak saturation number for this graph is not bigger than 5, but in fact it is equal to 5. This happens because we cannot get, since our final graph is connected, then our graph that percolates G should also be connected, so we can start only from connected graph. And in my example, the graph is a tree, so the minimum number is indeed 5. Okay, so let me now explain what happens when the pattern graph F is click. For example, when it is triangle, as on the previous picture. Then, as I mentioned, the weak saturation number is at most n-1. This happens because we can start from spanning subtree, and add all edges one by one. It is really easy to see that this is the case when we start, say, from a spanning substar. Okay, and is at least n minus 1 because the graph H that we start from should be connected, so it is exactly n minus 1. The question is what happens when we consider a clique of sides. And the conjecture of Bob from 1968 was that it equals to saturation number, which is exactly s minus 2 times n minus s minus 1 choose 2. And it was proved in several papers by Frankel in 1982, by Kalai in 1984, and by Lobos in 1977. Okay, and recently the same question was asked for the Geoffenki model. So now we remove from the complete graph edges independently with probability 1 minus p, so we get p model, and Karandi and Sudakov proved that with high probability we get a stability result that the weak saturation number of the binomial random graph equals to the weak saturation number of complete graph. So after removing edges independently, we still have the same weak saturation number. Okay. And in the same paper, they ask about possible threshold for this property. So the question is, does this stability result changes if we make p smaller? And they notice that if p equals to n to the some small negative number, then it should still preserve this stability property. But the question was about does there exist some threshold for this stability property, and if so, then what is the value of this threshold? And we particularly answered this question. In particular, we proved that the threshold exists. So there exists a probability. So here on the slide, I denoted by p0, such that if p is asymptotically bigger than this probability, then we have this stability property that the weak saturation number of the binomial random graph equals to the weak saturation number for the complete graph. But if p is asymptotically smaller, then it is not true. And we even have some interval, some lower and upper bounds for this threshold probability, but we cannot find its sharp value. So the bounds are like this. If p is at least n to the minus 1 divided by 2s minus 3 times log square of n, then we have stability property. And if p is this, smaller than some constant times n to the minus 2 divided by s plus 1 times some power of log, then there is no stability property. Here in the first estimate, this power of log can be improved for s bigger than 5, and we can I think we can even remove this log factor when s equals 3, but for s equals 4 we can do better than logarithm square of n. But for general s, this is the best what we have. Okay, now let me switch to ideas of some proofs. I will do that for I will prove this result for the case of triangle, and for complete graphs the proofs are very similar. First, let me consider p's that are very small. When p is asymptotically less than 1 divided by n, there are no triangles. This situation is very easy. We don't have any k3, so the weak saturation number equals to the number of edges, which is smaller than the number of vertices. And now let me consider p that are asymptotically bigger than 1 divided by n squared, but less than square root of 1 divided by n. And it is easy to compute that with high probability the number of triangles is less than half of the number of edges. So the expected number of edges is n choose 2 times p, and the expected number of triangles is 1/6 n cube p cube. So comparing this, you can see that the number of triangles should be with high probability less than half of the number of edges. That also immediately gives you that stability result doesn't hold. Okay, if I go back to the previous slide here, when s equals 3, yes, I think about the upper bound. So when s equals 3, I get 1/2. So we are already near this lower bound, but we also need to get some logarithm factor. To do that, let me state the following. So first of all, it is not difficult to see that with high probability there exists an edge that doesn't belong to any triangle, if P is like this, and that with high probability G of n P is 2 connected. So what it means is that if you find one edge that doesn't belong to any triangle, you can remove it. Your graph is still connected, but its saturation number can be only n-1, but you should add your edge back. You cannot do it because it doesn't appear in any triangle, so the weak saturation number is at least n, not n-1. Okay, here I do it formally. As we noticed, a connected spanning subgraph of complete graph is weakly K3 centered in Kn. And if a tree is weakly K3 centered in G of P, then it might contain an edge that doesn't belong to a triangle. So if we remove from H the edge E, then we get weakly K3 centered subgraph of G of P, from which we also remove this H. But this leads to a contradiction because H is not connected. It contains less than n-1 edges. Okay. Now about the upper bound. Let me go back. So what do we get here if you put s equals 3? Then the power of n is -1 divided by 3. Okay. Let me prove that if p is bigger than 2 times cubic root of logarithm of n divided by n, then we can get all the edges of G of P from some subtree. First of all, it is not hard to see that for such P, any 3 vertices have a common neighbor in the random graph, and that every pair of vertices induces, if you consider if you consider common neighborhood of any pair of vertices, then we get a connected induced subgraph. And from these 2 properties, it is not difficult to see that there exists a tree that percolates G of P. Okay, why? Let me explain it on this picture. So I consider an arbitrary vertex and consider all its neighbors and put in my tree all the trees that go from this vertex to the set of its neighbors, and choose the neighbors of this level arbitrary. So I just want to have all neighbors, all edges that go from the first vertex, and all the other edges are not so important, so I can choose them arbitrary to get tree of depth 2. First of all, let me look on this vertex and on its neighborhood, and let me try to recover this black edge. So when I look on the neighborhood, since I know that every pair of vertices has a connected neighborhood, this set induces a connected graph, and it means that I can recover all its edges that go from this vertex to this set, starting from the only red edge, because so I can draw a path that goes from this vertex to this one, and going by this path, recover all the edges from this vertex to the vertices of this path. Then on the next step, let me recover an edge between 2 sets. the bottom level. So I consider here these three vertices, the first two of this edge, and the last one is the first vertex. They have a common neighbor, and since these two blue edges are already recovered, I can recover also the missing edge between these two vertices on the bottom level, and we are done. Okay, and my last slide is about the proof of the existence of the threshold. It is rather tricky. I cannot, so I don't have time to explain all the details, but let me just explain all the basic steps. So first, if p is smaller than 1 divided by n log n, then there are no clicks, and the number of edges is smaller than n divided by 2. But the number of edges should be exactly the Wick's iteration number. So it cannot be equal to n minus 1. And so this case is very easy. The second case is also easy when p is between 1 divided by n log n, but asymptotically smaller than n to the minus 2 divided by s plus 1. Since the number of ks is smaller, say, than 1/2 of the expected number of edges, but the number of edges should be very close to the expected number. So the number of ks is smaller than 1/2 of the number of edges. It means that the saturation number is at least 1/2 times the number of edges. Okay, then what can we do next when p becomes bigger than n to the minus 2 divided by s plus 1? So here we do the following thing. So first of all, we consider the property Bs, that every pair of vertices have s minus 2 adjacent common neighbors. Of course, this property is increasing, and it is known that it has sharp threshold probability, and even the exact value of the sharp threshold is known. And if we consider intersection of this property with the property As that we study, the property of having Wick's iteration number of Wick's iteration number equals to here it should be Kn, to the Wick's iteration number of the complete graph, then intersection of these two properties should also be increasing, and so it has threshold, and it should be at least the threshold of the previous property, since we considered intersection of two properties. So it remains, and now the main trick is to prove that this new threshold of this intersection is threshold probability for new property, or for the property As, but not for the intersection. Yeah, it is not very easy and rather technical, so I want to skip these details and finish my talk here. Thank you very much.
Thank you, Maxim. There is a question in the chat. Istvan Toman wrote, is there a conjecture for the right threshold?
Yeah, okay. My opinion is that the right threshold should be close to the lower bound. So it should be close to, where is this lower bound? Just a second. Where it was here. Yes, so I think that it should be close to n to the minus 1 divided by 2s minus 3. But yeah, so yeah, I would say that this is my conjecture, but it can be false.
Okay,